Today we're going to be talking about local and absolute maximums and minimums and increasing and decreasing intervals. By the end of this video, you should be able to identify intervals on which the function is increasing or decreasing. You should be able to identify local maximums and minimums, identify absolute maximums and minimums, and you should be able to create a function given a set of characteristics. Let's look at some vocabulary. A local maximum is where a function changes from increasing to decreasing. So we're talking about the top of a hill. Okay, that would be a local maximum. A local minimum is where a function changes from decreasing to increasing. So we're talking about the bottom of a valley. An absolute maximum is the largest overall value of a function over its entire range. Sometimes this is one of the local maximums, sometimes it's not. But we are looking for the largest value. Similarly, the absolute minimum is the smallest overall value of a function over its entire range. So what is the lowest point on the entire graph? Increasing intervals are where a function increases as you go from left to right. Okay, so we're looking at sections where the graph has a positive slope. And a decreasing interval is where the function is decreasing from left to right, so where it has a negative slope. Okay, and left to right is extremely important for both of those. Let's look at some examples. So for this first function, we want to identify the local maximums first. So we're looking for where are the points that are at the top of a hill. That would be this point here. And we're going to write that as an ordered pair. So that is the point 2, 2. The local minimum is the point that's at the bottom of the valley. So that would be this point. And that is -1, -4. So make sure you write both of these as points. Now the absolute maximum, we are looking for the highest point overall. So it could be this local maximum, but this side of the graph continues going on forever. So when we talked about range last class, that side of the function is going to positive infinity, and positive infinity is not a number. So really there is no maximum. There is no absolute maximum for this graph. So you can either put none or you can put DNE, which stands for does not exist. For the absolute minimum, first you want to check the local minimum, and then you want to see if there are any other points that are lower. Well, on the right side of the graph, it's going to continue going down forever, and this side is going to go toward negative infinity. So just like we said for the maximum, there is no absolute minimum because that side of the graph is going to continue going down forever. So we can write none or DNE. One thing that you can use to check yourself is if you write out the range. The range for this function would be negative infinity to positive infinity. And those two numbers that you use in your range would be the numbers that you use for your absolute maximum and minimum. Okay, since both of those are infinity, then we have no absolute maximum or minimum. For the increasing intervals, I'm going to use a highlighter to help with this. So this section, whoops, this section of the graph has a positive slope. The graph is increasing, okay? So I'm going to highlight this whole section of the graph. And I'm going to kind of do increasing and decreasing intervals simultaneously here. On this part of the graph, it is decreasing. It has a negative slope. So I'm going to shade that whole section orange because it's decreasing. This section of the graph is also decreasing because it has a negative slope. It is going down as you read from left to right. So the key numbers that you look for when you are writing the increasing and decreasing intervals is where it changes from increasing to decreasing, and you are looking specifically at the x values. So right here at -1, the graph changes from decreasing to increasing, and here at 2, the graph changes from increasing to decreasing. And on this side of the graph, if we're looking at the domain, this will continue going all the way over to negative infinity. This side will continue going over to positive infinity. So between negative infinity and -1, the graph is decreasing. Then between -1 and 2, the graph is increasing. And then again between 2 and infinity, it is decreasing again. When you are writing increasing and decreasing intervals, you are always going to use parentheses. And this is interval notation. These are not ordered pairs, so don't get confused with that. But you always use parentheses because at this point, this minimum, the graph is not increasing or decreasing. If you get to calculus, you'll talk a little bit more about why it is that way. But at the point where it changes from increasing to decreasing or decreasing to increasing, it is neither of those. So we always use parentheses. And then since we have two intervals here, I'm going to use this union sign that we talked about last class to say that it is both of those intervals. Let's look at the next one. Our local maximum is this high point here, which is the point 0, 2. Our local minimum, there are actually two of them. There's -2, -3, and 3, -2. Now you'll notice that I put a comma between these, not a union symbol, because it is 2 points. It is not 2 intervals. The union is only used in interval notation. For our absolute maximum, we want to look for the highest point on this graph. Well, both of these arrows are pointed up, so they're going to go toward positive infinity. So there is going to be no absolute maximum. So you can put none or you can put DNE for does not exist. Now the absolute minimum, there is a lowest point on this graph, and that is here. This local minimum is lower than the other local minimum. So the way that we want to write this is that the local minimum is -3. That is the lowest that it goes, and that occurs at x equals -2. Okay? And if you think about the range of this function, the range would be from -3 to infinity. So we had -3 as our minimum. Infinity means that there is no absolute maximum. Let's shade where it's increasing and decreasing. So if I start on the left, whoops, This section of the graph is decreasing, so I'm going to shade that orange. Then the next section of the graph is increasing, so I'm going to shade that yellow. The next section is decreasing. Then the last section is increasing. So if we look at where all of these changes are from increasing to decreasing, whoops, this change is at -2, this changes at 0, and this changes at 3. And since there are arrows on both ends, this side goes to positive infinity, this side goes to negative infinity. So between negative infinity and -2, we are decreasing. Between -2 and 0, we're increasing. Since these are intervals, I'm going to put a union symbol. Between 0 and 3, we're decreasing, sorry. And then union here, between 3 and infinity, we are increasing. All right, next example. We have a local maximum at the top of a hill here. We'll call that 0, 3.5. And then we actually do not have a local minimum for this problem because there are no points where it's the bottom of a valley. For this problem, our absolute maximum is the same as our local maximum. So again, we want to look at how high does the graph go. So that's 3.5. So we're going to say that the maximum is 3.5, and that occurs at x equals 0. Since both sides of the graph are going down to negative infinity, we do not have an absolute minimum. If we shade where we're increasing and decreasing, if you start on the left, this side of the graph is increasing. And this side of the graph is decreasing. So it changes from increasing to decreasing at 0. So between negative infinity and 0 is increasing, and between 0 and positive infinity, it is decreasing. All right, for this next graph, we want to look at the local maximum, which again is the top of the hill. So that's this point, which is -1, 2. We have a local minimum at this valley point, which is 2, -4. But the absolute maximum, the highest point of this graph, is actually not our local maximum. It is this endpoint here. So we want to write how high does the graph go at that point? So it goes up to 3, and that occurs at x equals 5. Our absolute minimum, the lowest point on this graph, is the same as our local minimum. So the lowest that the graph goes is -4, and that occurs at x equals 2. Now if we highlight where the graph is increasing and decreasing, if we start on the left, the graph is increasing. Then it changes to decreasing. And then it changes back to increasing. So if we look at where those changes happen, changes from increasing to decreasing at 1, changes from decreasing to increasing at x equals 2. And then the tricky part that we need to be careful of is the graph starts at -4 and ends at 5. It does not continue on to positive and negative infinity. So between -4 and -1, oops, this should be a negative. -4 to -1, the graph is increasing. It is also increasing from 2 to 5, and then it is decreasing from -1 to 2. On our next function, our local maximum is this peak point, which is the point 2, 3. We do not have a local minimum because there are no points that are at the bottom of the valley. Our absolute maximum actually occurs at our local maximum. So the highest the graph goes is 3, and that occurs at x equals 2. Since the graph continues going down forever, we do not have an absolute minimum. If we shade where the graph is increasing and decreasing, if we start on the left, we're increasing. So this whole side is increasing. Then the graph starts decreasing. So it changes from increasing to decreasing at 2 and continues going out to negative infinity and positive infinity. So between negative infinity and 2, the graph is increasing, and between 2 and positive infinity, the graph is decreasing. One last example. If we're looking for local maximums, we're looking for points that are at the top of the hill. There are actually no local maximums on this graph. For local minimums, we are looking for points that are at the bottom, of a valley, which would be this point at 0, 0. Our absolute maximum, the highest place on the graph, is actually here. And that graph is at 4. And that's all points where x is greater than or equal to 2. Our absolute minimum, since the left side of the graph continues going down forever, there is none. So if we highlight where the graph is increasing and decreasing, if we start on the left, the graph is increasing on this section. Then the graph is horizontal. So I'm going to call that constant, and I'm going to color that a different color. Then the graph decreases. Then the graph increases again. Then the graph is horizontal again, so it is constant. And if I mark where all of those changes occur, on the left side of the graph, it's going to continue going out to negative infinity. Then it changes at 4, negative 4, changes again at negative 2, changes at 0, changes at 2, and then continues out to positive infinity. So our graph is increasing between negative infinity, negative 4, and also between 0 and 2. Then our graph is decreasing between negative 2 and 0. And the graph is constant between negative 4 and negative 2, and between 2 and infinity. Now we're going to take a look at how to draw some functions based on their characteristics. So if I am told that a function has a local maximum Now we're going to look at how to draw some functions based on some characteristics. So if I am told that this function has a local maximum at -2, 5, I'm going to plot that point. Then I know that it has a local minimum at both 4, or -4, 0, and 4, -4. Then you just want to connect the dots, making sure that your maximum and your minimums are correct. So this blue point here needs to be the bottom of a valley. This pink point needs to be the top of the hill. And then this blue point over here needs to be the bottom of a valley. And that's it. Then I want to draw a function for the next problem that is increasing from -infinity to 1 and decreasing from 1 to 5. So I'm going to start by shading this in. I know it needs to be increasing from -infinity to 1. Then it needs to be decreasing from 1 to 5. So it's going to change from increasing to decreasing at 1. It needs to stop at 5. And it needs to continue going over to -infinity on the left side. So there are actually infinite answers for this. A couple key things you need to make sure of. It needs to be only increasing in the yellow section. It needs to be only decreasing in the orange section. You need to make sure you have an arrow on the left side since it continues on forever. And you need to make sure that the function stops on the right side. So you could have a function like this. You could have one like this. You could have one that's very flat. Okay, there are infinite answers as long as you are increasing in the yellow section and decreasing in the orange section, and then stop where you need to stop.